Hello my dear students, I am going to start a lecture series on partial differential equations. This is useful for all engineering students and also BSc students, any undergraduate student level. Let us go into the topic of partial differential equations. So in this series we are going to learn how to solve partial differential equations. Right. So before that we will see what are partial differential equations and formation of partial differential equations. Right. So suppose you take a function z equal to f of xy. Here z is a dependent variable depending on x and y. X and y are said to be independent variables. They are independent variables. You can differentiate z with respect to x or you can differentiate z with respect to y. Suppose if you differentiate z with respect to x, what do we get? Dou z by dou x. So we name it as P, lowercase letter P. That is the standard notation. And Q is used to denote dou z by dou y. Right. So these two are called first order partial derivatives. Partial derivatives of z with respect to x and y. And you can also get second order or any other partial derivatives. Suppose if you take dou square z by dou x square, that means we are differentiating dou z by dou x again with respect to x, and dou square z by dou x dou y. That means we are differentiating dou z by dou y by again with respect to x. Or you can differentiate z with respect dou z by dou y with respect to y again. So these three are called second order partial derivatives. So these are denoted by RST. These three partial derivatives of second order are denoted by RST. Okay. These are second order partial derivatives of z with respect to x, y, that is independent variables. Okay. Now you'll see these, that means here you have to remember P, Q, R, S, T are always meant for dou z by dou x, dou z by dou y. R, S, T are meant for second order derivatives, dou square z by dou x square, dou square z by dou x dou y, dou square z by dou y square. Here x square, x, y square. In the same order you have to remember this R, S, T. Now we will see the formation of a partial differential equation. How to form a partial differential equation from a given function. So formation of a partial differential equation. Formation of partial differential equation is done in two ways: by eliminating arbitrary constants from the given equation. Also by eliminating arbitrary functions. So there are two ways you can eliminate the arbitrary constants and obtain the partial differential equation, or you can eliminate arbitrary functions and then you can find your partial differential equation. Okay. For example, let us start with eliminating arbitrary constants. How to eliminate arbitrary constants from a given function? So in this series, I am going to start. I want to cover all the problems in the examination point of view only. These series are meant for examination point of view, not deep into the subject. Okay. Of course, I cover the subject whichever is necessary. To what extent it is necessary, I cover. But main motto is to cover the series or topics in an examination point of view. Right. So let us see the first method, elimination of arbitrary constants. So in this, let us take first problem. Suppose you take z equal to ax square plus by square. Z equal to ax square plus by square. Then our objective is to eliminate arbitrary constants. What are the arbitrary constants here? A comma b are arbitrary constants here. A and b are arbitrary constants here. Okay. So our objective is to eliminate these two constants. Now how do you eliminate? First of all, you differentiate the given equation 1. Differentiate equation 1 with respect to x. What you will get? Dou z by dou x. We are differentiating with respect to x. Therefore, a is a constant. Derivative of x square is 2x. And there is no x in this term. So, derivative is 0. It is treated as a constant. Totally constant. So, we denote dou z by dou x by p. So, p equal to 2ax. Okay. Now again differentiate with respect to, differentiate equation 1 with respect to y. What you will get? Dou z by dou y. Now we are differentiating with respect to y. There is no y in this first term, 0. And b into 2y. It is 2by. So it is q equal to, because dou z by dou y is denoted by q, 2by. Now our objective is to eliminate a and b from these three equations, 1, 2 and 3. From these three equations, we need to eliminate a and b. So how to eliminate a and b? From this you can write a, from 2 you can write a, it is p by 2x, and from 3, third equation, you can write b equal to q by 2y. Now these two is substitute in the given equation 1. What you will get? You will get z equal to p by 2x into x square plus b. What is b? Q by 2y. Q by 2y into y square. Now you simplify this and you will get your answer. So how to simplify this? It is z equal to px by 2 plus qy by 2. 2z equal to px plus qy is the required answer. See, there are no a and b here, right? So therefore this is the required answer.
Okay. Let us take one more problem. Take another problem. Ax plus by plus cz equal to 1.
So what you have to remember here is Here z is always a function of x and y. Z is a dependent variable and x and y are independent variables. What you have to remember is z is always a function of x and y. Z is a function of x and y. So z depends on x and y. Z depends on x and y. So now you differentiate this equation 1 with respect to x and y. Okay. First of all, you differentiate with respect to x, you will get a into derivative of x is 1. There is no x in this. See, directly you may not see x here, but z is a function of x, right? Therefore, c into derivative of z with respect to x, dou z by dou x equal to, there is no variable on the right hand side, it is entirely 0. Constant derivative is 0. It is a equal to minus c dou z by dou x. Okay. But one thing we have to remember here is the number of arbitrary constants and the number of independent variables. You have to remember two things here. Case 1 is number of arbitrary constants is equal to number of independent variables. Number of arbitrary constants, in the previous problem, number of arbitrary constants a and b 2 and number of independent variables also 2. So in this case, you will get first order partial differential equation you will get. See, what is the answer in the previous problem? 2z equal to px plus qy. It is a first order partial differential equation because it contains first order partial derivatives p and q. Okay. When case 2, what is case 2? When number of arbitrary constants is greater than number of independent variables, you will get higher order, either second order or more. You will get a higher order partial differential equation. You will get higher order partial differential equation. So therefore, here in this case, you have A, B, C, 3 arbitrary constants, and that is greater than number of independent variables x and y. X and y is 2, right? So independent variables, number of independent variables is 2, number of arbitrary constants is 3. So 3 is greater than 2, therefore you will get a higher order. So that is how, even though you differentiate this another time with respect to y, what you will get? Here you will get 0, a into 1, b into 1, plus c into dou z by dou y equal to 0. From this also you will get v equal to minus c dou z by dou y. You see, from these two, you can eliminate a and b. From this you can write a, you can write b, but what about c? You cannot eliminate c. To eliminate c, we have to differentiate this or this one more time to get a second order partial derivative. So, either you take this one, that means you name it as 2, differentiate 2 with respect to x again. What you will get? 0, c into minus c into dou square z by dou x square. So dou square z by dou x square equal to 0 is the required partial differential equation. You can also differentiate this with respect to y, so that you will get dou square z by dou y square equal to 0. That is also a solution of this, right? That is also a partial differential equation you can obtain by eliminating arbitrary constant from this equation. And also you can get, you differentiate this with respect to y, then also you will get 0 equal to minus c dou square z by dou y dou x. So dou square z by dou y dou x equal to 0. So you have three equations here. You have obtained three solutions in this equation. In this case, dou square z by dou x square equal to 0, dou square z by dou y square equal to 0, dou square z by dou x dou y equal to 0. Any of these equations is a solution of the given problem. Okay. We'll move to the next problem. Find the differential equation of all spheres whose centers lie on the z-axis. Whose centers lie on the z-axis. So you take all spheres whose centers lie on z-axis. So center is lying on the z-axis. So any point on the z-axis is of the form 0, 0, C, right? So because the center is that, you take radius as r. All spheres whose centers lie on the z-axis. So how will be the equation? The equation is x minus 0 whole square, y minus 0 whole square, z minus c whole square equal to r square. Right? Equal to r square. So this is nothing but x square plus y square plus z minus c whole square equal to r square. Differentiate this equation 1 with respect to x. You will get 2x plus 0, there is no x in this, 2 into z minus c, because derivative of x square is 2x, derivative of something power n is n into something power n minus 1, 2 into z minus c power 2 minus 1, 1 into inner derivative dou by dou x of z minus c equal to derivative of r square 0. Therefore, x equal to minus of z minus c into derivative of z minus c is dou z by dou x minus 0. Right? So I send z minus c, this term to the right hand side. So this implies x equal to minus of z minus c into p. Now z minus c is eliminated, right? Similarly, you differentiate equation 1 with respect to y, you will get 0 here plus 2y plus 2 into z minus c into dou z by dou y equal to 0 again. right? So you will get y equal to minus of z minus c into q. Dou z by dou y is q. From these two, we can eliminate c because r is already eliminated. So what are the arbitrary constants in this problem? They are c and r, because c is also varying as the center of the sphere can be anywhere on the z-axis. So c is also varying. At the center changes, c changes. And there is no restriction on the radius of the spheres, right? There is no restriction. It's not constant radius. So you can take any sphere of any radius. So r also changes. So for each circle or for each sphere, c and r are fixed. But you take any sphere, random sphere, they change, right? So that is how c and r are the arbitrary constants in this problem. So therefore, r square is already eliminated. If you can eliminate c from these two, you need not take help of this, just these two. You divide these two equations, equation 2, equation 3, 2 divided by 3 gives x by y equal to p by q. So xq minus yp equal to 0 is the required partial differential equation, right? Obtained by eliminating the arbitrary constants c and r. Now let us take one more problem. Z equal to x square plus a square into y square plus b square. You take this problem. Here also two arbitrary constants a and b and two independent variables x and y. You will get a first order partial differential equation as a solution. Differentiating given equation 1 with respect to x. We are differentiating with respect to x. There is no x in this, so it is kept as constant. Right? Just differentiate this with respect to x. It is 2x. So p equal to 2x into y square plus b square. And differentiating equation 1 with respect to y, what we get? Dou z by dou y. There is no y in this, so it is kept as constant. Differentiate this with respect to y, it is 2y. So q equal to it is 2y into x square plus a square. Right? Now how to eliminate? Because still b is there in this equation, a is present in this equation. We need to eliminate a and b from these three equations. Right? From this you can write y square plus b square, you can obtain from this by as p by 2x. From this equation you can obtain x square plus a square q by 2y. Right? Now you can replace x square plus a square and y square plus b square in this equation and you can obtain the solution, right? So that you can eliminate a and b. Therefore, from 1, 2, 3 equations, z equal to q by 2y into p by 2x or 4xy z equal to pq. 4xyz equal to pq is the required answer, right? Now let us take one more problem. Z equal to x minus a whole square plus y minus b whole square plus 1. So this is also simple, very simple compared to just like the previous problem. You differentiate the equation 1, it is dou z by dou x. Here it is 2 into x minus a. There is no x in this, 0. This is also constant, this is also constant. So from this you can find 2 into x minus a equal to p, or x minus a equal to p by 2. Similarly, dou z by dou y equal to 0 plus 2 into y minus b plus 0. From this, 2 into y minus b is q. So from these two, you find x minus a as p by 2, y minus b is q by 2, right? From these three equations, eliminate a and b. Therefore, replace x minus a and y minus b in this equation. You will get p by 2 whole square plus q by 2 whole square plus 1. It is 4z equal to p square plus q square plus 4. Right? Let's take one more problem, which is z equal to, this is somewhat different problem. Z equal to a e power minus b square t into cos bx into cos bx. See here how many arbitrary constants are there? A and b, right? A and b, only two arbitrary constants are there, and two independent variables are there. X and t are the independent variables. Here z is a function of x comma t, right? Equation 1. Differentiate equation 1 with respect to x first of all. Dou z by dou x, we are differentiating with respect to x, so keep a into e power minus b square t as constant, right? Derivative of cos bx is minus sin bx into inner derivative of bx is b, because we are differentiating with respect to x. Derivative of bx is b into 1, which is b. So this is minus ab e power minus b square t sin bx. This is a typical problem. Let us see. Okay. Now differentiate equation 1 with respect to y. Dou z by dou y. Sorry, there is no y in this, t. Right. The other independent variable is t. Differentiate with respect to t. So a into cos bx is a constant. Derivative of e power something is e power something multiplied by inner derivative dou by dou t of minus b square t, right? Because we are differentiating with respect to t, derivative of e power minus b square t is e power minus b square t multiplied by derivative of inner function. So it is a into cos bx e power minus b square t into, what is the derivative of minus b square t with respect to t? Minus b square is constant. Derivative of t with respect to t is 1. Minus ab square cos bx e power minus b square t. So this is P, Q. Right? But you cannot eliminate A and B because you see minus AB, sometimes you divide the equation 2 and the equation 3, you will get the answer. But here e power minus b square t gets cancelled, A gets cancelled, 1b gets cancelled because that means you cannot eliminate b. And here you have sin bx and here you have cos bx. Right? So in these type of situations, to eliminate the other constant, arbitrary constant b also, we have to go for second derivative of this z with respect to x. Second order partial derivative of z. If you differentiate this again, what you will get? You will get cos bx. Here you have cos bx. Here also you will get cos bx. And one more b also will come, so that you will get b square also here. So from this you differentiate this again with respect to x. It is dou square z by dou x square equal to, differentiating this with respect to x, this is constant, minus ab e power minus b square t, derivative of sin bx is b cos bx. Right? So it is minus ab square e power minus bt cos bx. Now see, this is equation 2. Suppose this is equation 2. This is equation 3. Equation 2 divided by equation 3 gives dou square z by dou x square by dou z by dou t equal to same thing, minus a b square e power minus bt cos bx by minus a b square e power minus bt cos bx. So at one shot we are able to eliminate both the constants a and b. Right? So this implies the equation is dou z by dou t equal to dou square z by dou x square. So this is the required partial differential equation. So why we got the situation of second order partial derivative here is because the arbitrary constant, though there are two arbitrary constants a and b, one is a, the other one b is actually linked with two different functions. Right? Two different functions which are independent. You cannot eliminate or you cannot combine these two into a single function and bring b out of that. Right? So that is why we need to do second order derivative here. That kind of situations. Right? Now find the differential equation. Find the differential equation of all planes which are at a constant distance. From the origin. That means you take all planes, you take randomly one plane, right? From origin, the distance between the perpendicular distance, right? Distance to a plane from origin is nothing but the perpendicular distance. Let us name it as d. Right? So the equation of the plane, such kind of plane, is given by all those equations, all those planes equations are given by Lx plus My plus Nz equal to D. This is also a typical problem, very important problem. If the examiner wants to trouble you, they will give such kind of problems. Here D, what is D? D is the distance from origin to the plane. Okay. That plane can be anywhere around the origin, right? But distance is same, D is same. Because D is same to from origin to any plane, the distance is same. Distance is a constant. This is a constant. This is not a arbitrary constant. D is a constant. For every plane, L, M, N changes. So they are arbitrary constants. Okay. Here, L, M, N are actually direction cosines. Okay. Direction cosines of each plane. Okay. Direction cosines, they are nothing but, they are, LMN are nothing but the arbitrary constants here. So, are arbitrary constants. But in this particular problem, because you have three arbitrary constants, two independent variables x and y, three arbitrary constants LMN, right? You may be getting, you may be thinking that you will get a higher order, second order or higher order partial differential equation as a solution. But if you see, there is a property of direction cosines. Because they are direction cosines, they follow a rule L square plus M square plus N square equal to 1. So that N square can be written as 1 minus L square minus M square. Right? So that you can eliminate one arbitrary constant using this. How? Therefore, the equation 1 becomes Lx plus My plus root over 1 minus L square minus M square into Z equal to D. Right, N square is this, N is root over 1 minus L square minus M square. Now you see, you have only two arbitrary constants L and M in this equation. D is a constant, right? Now you take this equation. In this equation, two arbitrary constants, two independent variables. Therefore, you will get a first order partial differential equation as the solution, right? Now differentiate this equation with respect to x. What you will get? L plus 0 plus root over 1 minus L square minus M square into derivative of z with respect to x is dou z by dou x. Because d is a constant, derivative is 0. So what we got here is L equal to minus root 1 minus L square minus M square into P. Okay. Similarly, differentiate equation 2 with respect to y. What you will get? M equal to minus root 1 minus L square minus M square into Q, dou z by dou y. It is Q. So from these three equations, we need to eliminate L and M. So how to eliminate? Now let us write, from this equation you can write P equal to a P square equal to L square by 1 minus L square minus M square, and Q square. From this equation you can write Q square equal to M square by 1 minus L square minus M square, right? And you add these two, combining or adding these two, what you will get? P square plus Q square is LCM is same, 1 minus L square minus M square, numerator is L square plus M square. Now we add 1 on both sides, because you can take 1 minus L square minus M square to the numerator, and these two terms will be get cancelled. It is L square plus M square plus 1 minus L square minus M square by 1 minus L square minus M square. So it is 1 by 1 minus L square minus M square. Right. So from this we got 1 minus L square minus M square is 1 by 1 plus P square plus Q square. Right. You can ask me why you are doing all this. How do you know? Because I already practiced. I know it. And you also need to practice before going to exam, because we cannot expect this kind of problems you can solve instantly in the exam by using your creativity. Some problems we have to practice before going to the exam. You should know, otherwise you cannot attempt this problem in the exam, right? Now, so this is equation 2. In this, root over 1 minus L square minus M square is there, right? Now you divide the entire equation 2 by root 1 minus L square minus M square. Equation 2 divided by root 1 minus L square minus M square. What happens? L by root 1 minus M square, L square minus M square, x M by root 1 minus L square minus M square y plus z equal to d by root 1 minus L square minus M square. Right. Now what is L by root 1 minus L square minus M square? It is minus p. Right. It is minus p. So minus px M by root 1 minus M by root 1 minus L square minus M square is minus q. So minus qy plus z equal to, and what is root 1 minus L square minus M square? 1 by root 1. So it is 1 minus L square minus M square is 1 by root this. So how do you write this? It root over 1 minus L square minus M square is 1 by root 1 plus p square plus q square, right? Root, you take root on both sides, square root, it is root 1 minus L square minus M square is 1 by root 1 plus. Now we are successfully eliminated all m and n, right? There are no L and m in this. So this is d root 1 plus p square plus q square, z equal to px plus qy plus d root 1 plus p square plus q square is the required answer. You understood the answer? Okay. Here you should not get a doubt that d is not an arbitrary constant, d is a constant, right? That need not to be eliminated. L and m are to be eliminated. Okay. Now we will move to one more problem. X minus a whole square plus y minus b whole square equal to z square cot square alpha. When you see this kind of problems, you maybe get confused of what is this cot square alpha here, right? There is no importance of that cot square alpha. We have arbitrary constants a and b. independent variables x and y. Okay, that is just to confuse the student. Differentiate this equation 1 with respect to x, 2 into x minus a into derivative of x minus a 1, 0, there is no x in this, 0, equal to derivative of z square is 2z into z derivative is dou z by dou x into cot square alpha. So 2 gets cancelled. X minus a is z into p cot square alpha. Similarly, when you differentiate equation 1y with respect to y, you will get y minus b equal to z into q cot square alpha. We need to eliminate a and b, and we have x minus a and x minus b. Just replace them here in this equation. Zp cot square alpha whole square, zq cot square alpha whole square is z square cot square alpha. So it is z square p square cot power 4 alpha, z square q square cot power 4 alpha, z square cot square alpha, z square gets cancelled, cot square alpha gets cancelled, p square plus q square is 1 by cot square alpha, right? You have cot square alpha 1 equal to 1, it is p square plus q square is tan square alpha is the required partial differential equation. Okay. So one more problem, which is the last problem of the elimination, this topic, elimination of arbitrary constants. We have one more problem. Cover this, everything will be done. Right. The equation is not directly given. The equation is all spheres of given radius are having their centers in the xy plane. Now the centers are there in the xy plane. Center is here, you have a sphere of radius r. All spheres are having the same radius, given radius, same radius. We have a family of spheres here. All the spheres are having same radius, but center changes. Center of each sphere changes. Because they are all, the centers are all on the xy plane, C must be 0. That means z coordinate must be 0. A comma B comma 0. Right? A, B, 0. A1, B1, 0. A2, B2, 0. Like that. So, the center, if it is A, B, 0, all spheres of constant radius R having centers in xy plane, right, in xy plane. Therefore, this sphere equation will be like x minus a whole square plus y minus b whole square plus z minus 0 whole square equal to r square. Here r is constant, right? So differentiate with respect to x, you will get 2 into x minus a, 0, 2zp equal to 0. Z square derivative is 2z into derivative of z with respect to x is p. So from this we have x minus a equal to minus zp. Similarly, differentiate this with respect to y, you will get y minus b equal to minus zq. From these two, you substitute into back into this equation, what you will get? Minus zp whole square. In place of y minus b, you put minus zq. equal plus z square equal to r square. So it is z square into p square plus q square plus 1 equal to r square. You need not eliminate r because it is not an arbitrary constant. It is a constant, right? It won't change from sphere to sphere. So that is why it is a constant, right? So this is all about eliminating arbitrary constants from a given function and forming a partial differential equation. Okay. Thank you. In the next class, I am going to cover elimination of arbitrary functions from a given function and to obtain or to form a partial differential equation. Okay.